ranging from the microscopic world to the world visible to the naked eyes. There's an invariant relation between a predator and its prey. This relation undoubtedly plays a significant role in maintaining the balance of nature and has interested researchers. The main source of interest is the balance of population that's maintained between the creatures, and it's a complicated relation indeed. One of the first and most notable models created for the same was the Lotka-Volterra model. Let's try to understand it with an example. Consider an environment containing foxes and rabbits, where the rabbits are hunted by the foxes for food. It assumes that if the foxes are absent, the rate of growth of the rabbits depends on its current population. In other words, it grows exponentially. Now, as we include the foxes, there will be a decrease in population of rabbits, and that will be proportional to both the animals' populations, as more rabbits imply more food for the foxes, which means a rise in number of foxes, which leads to a decrease in rabbit population. To include that, we would subtract the following term. For the case of foxes, it's clearly dependent on both the rabbit and the fox population, just like the previous case, except the sign changes, and it depends on the consumption of the rabbits, as this is the case of growth of foxes. Considering the competition among the foxes, a large number of them would mean more competition, which results in decline in fox population. For that, we subtract this term. This system of differential equations is called Lotka-Volterra equations, and it gives us a simple idea about the population dynamics of the one prey, one predator system. Now, there's something interesting in the predator versus prey plot. Considering certain initial conditions, the plot forms a closed figure. This intuitively makes sense, as at one point the rabbits are high, the foxes will get more food, which results in its increase, and an increase in foxes imply more competition, hence they get lower in number, which is again good news for the rabbits as they can increase in number, and the cycle continues. If we have a look on the vector space it's lying on, we know that for different initial conditions we get a closed figure around a certain point. This point is special as it's the point of equilibrium. This is the situation when no change occurs in the animal populations. This equilibrium point we get here is called a center. And if we have a look on how the population versus time plot looks like, we know that it forms periodic oscillations. But there's one problem with this idea. We'd assume that the population of rabbits would grow exponentially if there are no foxes. Considering there's only limited food available for the rabbits, Volterra modified the equation by subtracting this term to balance out things. This change will also affect the rate of change of fox population. Therefore, the new set of differential equations look like this. Now, if we have a look on the predator versus prey plot, we get a spiral, which eventually gets to a point. Interestingly, regardless of the initial conditions, we eventually end up at the same point. Plot of the population versus time shows us the population don't exhibit major fluctuations. Rather, it's a damped oscillation, and the point the spiral gets into is the equilibrium population, where eventually the population gets to for both the animals. This equilibrium point is also called a stable focus. This was the case of one predator hunting and feeding on one prey. Let's go a bit deeper and extend the food chain where we include the plants on which the prey will be feeding on, say carrots. Things get interesting in this case. The most frequently used model uses the fact that consumption rate of an animal rises with pure density of its food, but then it gradually decelerates and becomes constant. Now let's talk about the differential equations. The rate of growth of plant depends on its current population, and keeping the carrying capacity in mind, we multiply the 1 minus p term. Clearly, the prey feed on them, hence they must decrease depending on the rate of plant consumption. To include the same, we subtract this term, where f1 is a specific function representing the consumption of the plants. For the case of prey, it depends on the current population and the amount of plants available for growth. Including the predators in the system, they will decrease. This decrease depends on the prey population and the predator population, similar to the one predator, one prey model, and we will represent it in the following way. Finally, we will also have to include the death rate of the prey. For the case of predators, their population increases depending on the predator population and the population of its prey. To be specific, the consumption rate of their prey. Further, we will have to include the death rate. These three equations can now be used to model the population dynamics. The functions we mentioned can be written in the following manner. Note that to incorporate the idea of consumption rate becoming constant gradually, there's a u term in the denominator of the function. Also, keep an eye on this b1 term, as we will be using this in the future. Interestingly, it doesn't behave the way its one prey, one predator counterpart did. If we look at the phase plot, it forms a structure like this. This might not look exactly as it should for the error in precision and the number of times I'm running the simulation on my machine. A better plot looks like a teapot-like shape. Note that if we start at the teapot handle, we spiral down along the pot and finally enter the narrow part. From the population's perspective, the foxes first crash with fluctuations in rabbit and carrot populations. As the foxes increase, the population fluctuations of the rabbits and carrots decrease until carrots drop in number, which further leads to a crash in fox population and increase in carrot population, and the process continues. Now have a look at the population versus time plots. Note how they don't look periodic, rather random. If we plot the peak fox population in each cycle against the b1 term we defined earlier, we note that it declines gradually, then splits up into half and becomes a chaos. The population versus time plots we saw earlier was simulated taking b1 equal to 3, hence the show of random behavior makes sense. So what is this b1 term which causes the chaos? Remember the assumption about the food consumption we made earlier? The term assigned to it is type 2 functional response. The expression we have for the same is the following. The term A denotes the rate at which the animal encounters its food per unit of its food density, and the average time spent on processing a food item is denoted by age. If we compare this expression with the f1 function we note that b1 equals AH. The encounters of rabbits with the carrots per unit of its density and the time taken by the rabbits to process the food can cause a chaos in the animal populations. Another interesting setup had been made for studying the populations of microbes, where there was one predator and two preys, one of which is preferred more by the predator but has a faster growth rate, feeding on the nutrients in the culture medium. Every so often, the nutrient solution is poured into the environment, which causes an overflow of mixture of microbes and nutrients, therefore lowering the number of microbes. This is also known as dilution. The rate of change of nutrient concentration firstly depends on the concentration of the remaining nutrient in the reservoir, and further depends on the consumptions made by the microbes. For each microbe, the rate of growth depends on the consumption of the nutrients and the decrease in the presence of the predator, just like in the previous case, where more prey implies more predator, hence greater decline in prey population. Finally, we have the dilution factor, which represents the decrease in population after the dilution. Side note, I equals 1 or 2. For the case of predator, the growth depends on its consumption of the other two microbes and the decline occurs for the dilution. The consumption here as well respects type 2 responses. It is worth noting that this model might look quite similar to the fox rabbits carrots model, except there is another competitor for rabbits. Most significant is the fact that the nutrients can't reproduce unlike the carrots. Hence, its change in concentration does not depend on the amount of nutrients in the environment. Apart from the dilution rate and nutrient concentration, all the other parameters are predetermined as they represent biological properties. For the case when D equals 0.035 per hour, the population versus time plot shows periodic oscillations. When D equals 0.055 per hour, we get a situation where the populations reach an equilibrium. However, when D equals 0.045 per hour, the plot seems random. If we note the equilibrium concentration of the nutrient versus the dilution rate, we note that it first increases, bifurcates, oscillating between two equilibrium concentrations, divides into 4 and becomes a chaos. Therefore, the rate at which the nutrient solution is poured into the environment has the power to cause chaos. A common myth that was once prevalent was about the rare occurrence of chaos in nature. On the contrary, it is more common than we thought. Researchers examined 172 datasets from the Global Population Dynamics database and found chaotic behavior in more than 30% of the populations, insects and planktons being most chaotic. They noted the more short-lived a species is, the more likely it is to expect chaos in their population. Therefore, it becomes extremely important for us to recognize the existence of chaos, else we might miss a lot on short-term possibilities.